Hi guys, welcome to my channel. So today I'll be solving this GFG problem of the day, which is binary tree to doubly linked list. So again, the difficulty is marked as hard, but the problem is so simple if you all know the approach, like how to approach this problem or what's the intuition behind it. Once I'll be explaining this code, the code will be like cake work for you all to write. So let's read the problem. So the problem says that you are given a binary tree and you have to convert it into doubly linked list. Now, a binary tree has its left pointer, you all can see, has its right pointer. So we have to consider the left pointer as the previous pointer and the right pointer as the next pointer, and we have to convert it into a doubly linked list. The order of the nodes in doubly linked list must be same as the order given in binary tree. Okay, first 25 is coming, then 12 is coming, then 30, then 10, then 36, then 5, means in order. You all can see this is given a node of in order traversal. Okay, H is the hierarchy and space is used implicitly for the recursive stack. Okay, so let me explain you what it is trying to say. Okay, so whenever binary tree comes to our mind and whenever we see the question of binary tree, then we only have traversals. Okay, now what traversals? Pre-order, in order and post order, because anyhow we have to solve the problem, then we have to use the traversals. Okay, so in this the question is mentioned that we have to convert this binary tree into doubly linked list by using the in order traversals. Okay, clear? Okay, so so let's traverse it. We are standing on 10, we are moving to 12. Okay, now again we are standing on 12, we are moving to 25. Now if we are standing on 25, the left node is null. Okay, so what are the operations we need to perform is 25 left is null, 25 right is null. Okay, 25 left is null, 25 right is pointing to 12. Okay, so what is the previous node which we have came to 25 is 12. Okay, so what we have to do, we have to consider the right pointer and make it to 12. Okay, so let's make it to 12. Now we have explored 25. Okay, we have explored 25. So what is the node from where we have come to 25? It was 12. So we have made the right pointer to the 12. Now after going back to 12, now exploring its right part, 30. 30's left is null, 30's right. Now what is 30's right? Okay, so before that, standing on a particular node, we have to cover its left, we have to cover its right. Now 30's left is null. What we have to do, we have to mark 30's left as 12. Okay, somehow we have to mark it as 12. Now one thing that is common, which is this is the node from where we have come to 30. Okay, this is the node from where we have came to 25. Okay, so now 30's left is equals to the node from where we have come to 30. Okay, done. 25 right is equals to node from where we have came to 25. Okay, so now last visited node is 30. So let's mark it as last visited node. Okay, so now the recursion call will goes like, I have explored its left, I have explored its right. Now coming back to 12. Now I have explored its left, I have explored its right. Now coming back to 10, I have explored its left. Now if I am standing on 10, because you all know that if in order what we are doing, we explored left, we do operations, then explore right. Now for the node 10, we have explored its left part. Okay, now we have to do the operation. In operations, what we need to do is we have to make the current node left as the last visited node. Okay, you all can see that if we are standing on 10, what we have to make its left as 30, means the last visited node is 30. So let's make it. Okay, so I have made this as left. Okay, now the last visited node, which was 30, its right is pointing to 10, means the last visited node which we have stored somewhere, its right is pointing to the current node. Okay, so let's make it. Okay, so I'll be explaining it one more time by code, like how code is working. Okay, so now our current pointer is standing on 10. Okay, so let's remove this last and we have done the operations. Okay, so last visited is this. Okay, we have covered his left, we have covered the operation, now covering its right. Okay, now standing on this node we have to go again left. Now standing on this node we have to go again left. Now coming back from left means left done of 36. Now the turn is to do the operation. What is the left, what is the last visited node which we have covered before 36? It is 10. So what we are going to do is 36 left is equals to 10. You all can see that here 36 left is equals to 10. Now I am explaining you how you are thinking of, like, how it is converting, like binary tree to doubly linked list, how we are converting. I'm not explaining you the code or the approach. Okay, so 36 left node will be pointing to 10. Now last visited right pointer will be pointing to this. Okay, this looks somewhere messy. Remove this because left pointer is pointing to 30 and right. Every node has its two pointer. Okay, let's take the example of this node. Okay, so one node, two nodes are going out of this and two nodes are coming towards this. Okay, let's see. If we are standing on 30, two nodes are going out of this and two nodes are coming towards this. Okay, we are successful. We have marked 10's left is equals to 30, 10's right is equals to 36. Okay, 10's left is equals to 30, 10's right is equals to 36. Okay, 36 left is equals to 10 and 30's right is equals to 10. 36 left is equals to 10 and 30's right is equals to 10. Okay, we have successfully made it. Okay, so now let's see how we can approach this by using code. Okay, done. Okay, so let's start traversing. Okay, so if we are standing on this node, we are standing on current node. Now I am explaining you with the context of code. Okay, so if we are standing on 10, we'll be moving it to 12. Okay, we have explored left of 10 and okay, so every node has its left. Okay, so now we are standing on 12. Now we have to cover its left, just simple in order traversal. Now we are standing on 25, we have to cover its left. There is no node coming back to 25. Now if we are standing on 25, we'll be marking it as previous. And one more thing, we have to return the head of the linked list, node star. Okay, so this is the head of the linked list, so we have to make the track of this. So this is the previous and this is the head which we are marking in on 25. Okay, so now moving again, we have explored its left 25. Now moving to right of this. Okay, null, then again coming back to 25. Okay, we have explored its left and right. So whenever we are at the bottom left, then we know that we have to perform this operation once, because we have to mark this node as head and start this node as previous. So this is the one-time operation that we are going to do when we are at the extreme left of a binary tree. Okay, so we have marked it as left. Now let me remove this traversal. I have explored its left and right, marked 25 as head and started our operations and marking it as previous. Now I've explored left, right. Now coming back to again 12, because I have explored its left. Now I have to do some operations. Okay, what are the operations that I need to do is I have to mark, you all can see from here. Okay, so you all can see 12. 12's left is 25. Okay, so what I am going to do is, let me remove this. 12's left is 25. Remove this and 12 left as 25. Now this is my previous, this is my root node. Remove this. Currently I'm standing on this, means if I complete the left part, I'll be doing the operation, then moving to the right part. Now 12's left part is already explored. We have came to 12 from here, so we are doing the operation. 12's left part is marked as previous right part is marked as 12. You all can see from here, previous, we are standing on 25, its right part is marked as 12. So let me remove this and mark this node as root. Now after doing the operations, 12 has become our previous node, so marking it as P. Now our previous node is 12. Let me remove the iteration. Okay, let me remove this, and 12 has become our previous node. Now from 12, where all we can go? We can go to 30, more like doing its right operation. From 30, now what we have to do? We have to go its left part. Okay, no node, coming back. After exploring the left part of 30, we need to do the operations. Okay, what are the operations that we need to perform? We have to mark its 30. Okay, let's see in the doubly linked list. 30's left is equals to 12. 30's left, which is pointing to null, we have to make it to 12. So how we can do? We are standing on 30, means current root, our current pointer is at 30. 30's left is equals to previous. Okay, let's remove this, and 30's left is equals to previous. We have done the operation on root. Now from previous, what we have to do? Okay, so 12 right is also pointing to 30. Now 12 right will be pointing to 30. Okay, so now you all can see that there is 2 pointers that is coming towards the node. There are 2 pointers that is going out of the node. Okay, we are successful in marking it. Now you all can examine one thing, that at the particular node where we have previous node and current root node, what are the operations we are doing? Okay, previous node and root node. Okay, so what we are doing is we are marking current left is equals to previous, and previous right is equals to root, and marking root as previous as root. Because let's see in this example. Okay, we have covered 30's left, we have done the operations. Now we have to move further. Before moving further, this is the last node that we have explored. Now this has become our previous node. Let's remove this, and this has become our previous node. After going back, okay, I have explored its left, done the operation, explored right. Now moving back, coming to 12. Now I have explored its left, I have explored 12's left, explored it, done the operations, 12 right explode. Now I have to move back to 10. Now moving back to 10 means done the left part. Okay, now it's turn to do the operation on 10. Now what are the operation that I need to do? I have root pointer pointing here, previous pointer here. Current left is equals to previous. This is my current node 10, or I can say the root node, or I can say the current node. Okay, C, let me mark it as C. Now current left is equals to previous. Let me remove the current left. This is the traversing part. Let me remove this. Okay, current left is equals to previous, means current left is equals to previous 30. Let's see in the this current is turning on this. Current left is equals to 30. Okay, current left is equals to 30. Now next step is previous right is equals to root. Previous, this previous 30, this right is equals to root, means current. Not make it root, make it as current. You all will be confused. CU current. This has current. Now previous right is equals to current, means previous right is equals to current. Now what I have to do? Previous is equals to current, means we are standing on 10 and we have explored its left, done the operations, and we are moving towards right. Before moving towards right, let's mark it the previous node. Okay, so let's remove this, let's mark it as previous node. Now we have to do further operations. We go right, then according to in order, we again go to left, because left operation right. Okay, so we are standing on this node, we have to do left is null. Okay, left is null. We came back. Now after exploring its left, we have to do the operation. Now what operations we need to perform? You all know. Current left is equals to previous, means current, this is current, current left is equals to previous. Now current left is equals to previous. Okay, previous right is equals to current, previous right is equals to current. Now previous right is equals to current. Now let's match this. 36 left is equals to 10, 36 left is equals to 10, 10 right is equals to 36, 10 right is equals to 36, and we can see that on a particular node 2 nodes are coming and 2 nodes are going. Okay, we have successfully completed 10. Now let's move. Before moving, what we have to do, previous is equal to current. Now previous will be pointing to current. Okay, this will become previous. Now moving back, coming to this node 15, we have explored its left part. Okay, done. Now coming to the operation on 15, what we have to do, current left is equal to previous. We are standing on 15, means current left is equal to previous. Let me remove this and mark current left is equal to previous. Now previous right is equal to current, previous right is equals to current. Okay, let me remove this previous right is equal to current and previous is equals to current. Now previous is equals to current. This is already marking to the right. Okay, let's see that we are standing on this 15. Let's match it. If we are standing on 15, 15 left is equal to 36. Okay, 15 left is equal to 36. 36 right is equal to 15. 36 right is equal to 15 and 15 right is equal to null and 15 right is equal to null. And finally we are like this. Okay, I have to update head pointer. So this is our head node, and finally we will be returning the head node of the this linked list. And finally we have converted our pointer to the doubly linked list. So this is how we are solving this problem. Okay, so now let's discuss the time complexity and space complexity of this problem. So time complexity, what is the time complexity of this problem? Because we are visiting each and every node once, so the time complexity is big O of n. Okay, so the time complexity will be big O of n. Now what is the space complexity? Now you all will be wondering that the recursive stack takes the space. Okay, so we have visited all the nodes, so according to you all the space will be big O of n. But no, what is the space complexity here is big O of h. How big O of h? Because the recursive stack will only take the space as the height of the tree. Why? Let's see. Okay, we have visited 10, we visit to 12. Okay, let me write it as 10. Now we are visiting to 12. Okay, let me write it as 12. Okay, now we are visiting 25. Let me write it as 25. Now after visiting 25, we have explored its left, we have explored its right, and now we are moving towards back. Now moving back, this is get destroyed. Okay, 25 gets destroyed. Now coming back to 30. Now let's write 30. Okay, the height of the tree by the way is 3. Okay, so coming back to 30, explore 30's left, explore 30's right. Now coming back to again 12. Now 30 is destroyed. You all will be noticing that the stack size will never be increasing more than the height of the tree, so our space complexity will be big O of h. This is what the time complexity and space complexity of this problem. Okay, so here is the code and let's see how we are solving this. Okay, so what we are doing here, I have told you to initialize one previous pointer and one head pointer, because I have to mark this as head and starting from the previous pointer, because we are starting from left and traversing towards the right. Okay, now I have initialized a count variable. Why I have initialized a count variable? Why? Because once I'll be reaching at the current end, then I have to do the one-time operation. Okay, one-time operation, which is I have to mark this as previous and mark this as head. Now I have passed the head pointer, previous pointer, and count and root, and finally our head pointer will be storing our answer, and I have returned the head pointer. Let's see how this recursion calls are working. Okay, if base case root means we have to return. Now the left part will be moving root left. Okay, so this call will go, then again call will go, again call will go, and we'll be moving towards the entire left of the binary tree. If we move at the entire left of a binary tree, the count is equal to 0 as we have passed. Now we'll be doing that one time operation, which is head is equal to root, previous is equal to root. Now moving count plus plus, so that the pointer will never enter in this if, it will always enter to this. So what we are doing in else is root left is equal to previous. You can see that current left is equal to previous. Current I have taken as root. Okay, previous right is equals to root. Okay, previous right is equals to root means current, this is current, and previous is equals to current means previous is equals to root, previous is equals to root, and finally doing the right call. And this is how we have solved this problem. Okay, so let's run this code. Okay, so let's submit it. Okay, so it has passed all the test cases. So that is how we are solving this problem. So thank you for watching and having patience. So thank you.